Okay, so what we just went over was the definition of a finite state machine. And a finite state machine is a sequential circuit, so using flip-flops, that can be represented by using a finite number of states. So the machine can only be in certain states. It'll have a certain condition. So it'll have this condition or that condition or that condition. And the difference between a Moore and a Mealy machine is if there's an output for the machine, a Moore machine, the output only depends on what the current state of the machine is. That'll tell you what the output is. For a Mealy machine, the output depends on both the state and the input. Okay, so now let's take a look at a particular circuit that we're going to have to do some work with. So this circuit has one input, W, and one output, Z. All changes in the circuit occur on the positive edge of the clock signal. And then number 3 tells us what our output is. The output Z is equal to 1 if during the 2 immediately preceding clock cycles the input W was equal to 1. Otherwise, the value of Z is equal to 0. So you want to look at the previous 2 clock cycles. If they were both 1, then your output is 1. Otherwise, it's 0. And you usually have a start condition, a reset, and our reset here is going to have Z equal to 0. Okay, so now when we get to time 1, are the previous 2 inputs 1? No, there's only one input and it's 0, so that's a 0. When we get to time 2, we look at the previous 2 inputs, they're 1 and 0. They're not both 1, so that's a 0. When we get to T3, I look at the previous 2 inputs, 0, 1. They're not both 1, so I'll have a 0. When I get to T4, I look at the previous 2 inputs. The previous 2 inputs are T2 and T3. They're not both 1, so it's 0. But I get to T5, and I look at the previous 2 inputs, T3 and T4. They are both 1, so my output is 1. But then I have that darn 0 in there. So now when I get to T6, my previous 2 inputs are not both 1 anymore, so it's 0. When I get to T7, the previous 2 inputs are 1 and a 0, so that's a 0. When I get to T8, the previous 2 inputs, T6 and T7, are both 1, so that's a 1. And when I get to T9, the previous 2 inputs are both 1, so that's a 1. And when I get to 10, my previous 2 inputs are a 0 and a 1, so that's a 0. So, did everyone see how I came up with those? All right. So now what we have to do before I can do this state diagram is I have to figure out what my states are for this machine. So I'm going to have, because I'm told there are 3 states, I know there are 3 states, but if I weren't told, I would just have to try to figure it out. So I want to think about what are my possibilities and in what sort of ways can I get towards my goal of having 2 1s. Well, if my last one was a 0, I'm not on my way towards getting 2 1s. So I'm going to say state A is previous input is 0. Now, my next possibility is I'm on my way to getting 2 1s, but I don't have 2 1s quite yet. So this would be the previous input is 1, and the input before that is 0. So an example of that is if I look at my table right here, if I'm at T2, my previous input was 1, and the input before that was 0, and that would be the state that I'm in. If at T2 I'd gotten a 1 instead of a 0, then that would have been a winner. So look at T4. T4, my previous state is a 1, the state before that is a 0. But that means because then when T4 is a 1, then I'm going to get my 2 1s in a row. So state C is previous 2 inputs are 1. Okay, so W is our output. W is our input. W is our input and Z is our output. And this is how you draw your state diagram. So this first state, we're saying state A, our previous input is 0. So if we are in state A, what's our output? 0, because our previous 2 inputs were not 1. The only way to get an output of 1 is if your previous 2 inputs are 1. Let's go through and fill in all these Z's. So for B, B is my previous input is a 1 and the one before that is a 0. So what's my output?
0.
Also 0, because my previous 2 inputs were not 1. For C, my previous 2 inputs are 1. So what's my output? 1. And you see how that depended only on what state I was in. We haven't done the inputs yet at all. Okay, but now we'll do the inputs. So for when you're drawing one of these, what you have to do is you have to say for every state, what happens if I get an input of 0 and what happens if I get an input of 1. And if you have one that's 2 bits, you have to go through 0, 0, 0, 1, 1, 0, and 1, 1. So let's look at this first state. My previous input is 0. If I get a 0, if my next input is a 0, what state am I going to be in? I'm still going to be in A, because when I get a 0, then my previous input is 0. So when W equals 0, I go back to state A. Okay, what if I get a 1? It goes to B, because now I have a 1 and a 0. So now I'm on B. What happens on B if I get a 0? Go back to A, so that's this arrow. And what happens if I get a 1? C. Now, let's say I'm in state C and I get a 0. You go back to A, and let's say I'm in C and I get a 1. It stays. Okay, so y'all are going to need to, actually I think I have it written down. So you might have to look back at what we had. So this is our state table. So the thing we did a minute ago was state diagram. This is state table. So for W equaled 0, whenever W equaled 0, we always went back to A. So A. When we were in state A and W equaled 1, we went to B. When we were in state B and W was 1, we went to C. When we were in C and we got a 1, we stayed in C. And our output was 0 for states A and B and 1 for C. Okay, so y'all need to stop me if you have a question. Good? All right. Okay, so the next one, the state, I'm trying to think of what he calls it, the state assigned table maybe? The state assigned table. This is really, really easy. So once you've done the state table, now you are representing your states now with a binary number, A, B, or C. And all you have to do, so what this is telling us is A is 0, 0, B is 0, 1, and C is 1, 0. You can pick yourself what you want them to be, or you might be told. In this instance, we were told. And all you have to do is replace your A's, B's, and C's in your state table up here with their number. So A, everywhere there's an A, I'm going to put a 0, 0. And B was 0, 1. And C was 1, 0. And I don't have a fourth state, so this is going to be a don't care. And then my output Z is going to be, that's going to be the same, 0, 0, 1, except now I have a don't care. Okay. Now we're going to use Carnot maps to derive expressions for y1, y2, and z. So I always have to kind of remind myself I'm doing y1. That's what I just highlighted there. Those are the values that I'm going to be filling in on this table. The highlighted, those zeros and D's and ones, that's what I'm going to be putting in here because I'm doing Y1. And then Y2 and Y1, that's these numbers over here. And then W shows up here. So I see that for W equal to 0, I have, so for W equal to 0, so here's where W equals 0, right there. I have a don't care at 1, 1, and the rest of these are zeros. When W equals 1, I have a don't care at 1, 1. And I have a 1 for 0, 0. I have a 0 for 0, 1. And I have a 0 for 1, 0. So all I have is this 1, 1 here. So y1 equals y2 bar, y1 bar, w.
How is it 0 at 0, 1 when w is 1? Oh, we're only looking at w.
You only look, yeah, that's what I was saying. I have a hard time with that. That's when I So here I use the highlighter. If I'm doing it on my own, it's like I circle the things. Sometimes even write it out separately because it's so easy to get confused as to which numbers you're looking at. Okay, so now we'll do Y2. And so let's see, what did we have here? We had okay. So now we're looking at Y2. And I can see when W equals 0, that's this first column, it's a don't care at 1, 1, and it's zeros everywhere else. And when W equals 1, it's a don't care at 1, 1. It's a 0 at 0, 0. And it's 1s here and here. And I'm going to give y'all a second to see if y'all can remember the best way to do the Carnot map with that. What's our expression going to be? WY1 or WY2, yep. So what we do is we want to cover all our ones with as few circles as we can, but as big as we can. But the size of the circle has to be 1, 2, 4, 8, 16. So the best we can do is to get these two together and these two together. And so, because we can use the don't care if we want to, we don't have to. So these two in the middle here, what they have in common is Y1. So Y1 is 1 for both of them. And W is 1. Or what these two have in common is Y2 is 1 for both of them, and W is 1 for both of them. And then because we're going to be building a circuit, it's probably going to be a little nicer to write it like this, because that would only use 2 gates instead of 3.
Why do you use Y1 and Y2 again if this is only the Y2 Carnot map? Or did you combine the two?
Okay, so this first circle here. I look at, so I'm going to look at this number and this number and this number. And I want to see everything in that circle, what do they have that's the same? Well, they all have this second one is a 1, and that's Y1. And they also both have W as 1, so that's W. Okay, so that's that circle. But then I have another circle, and I join them with a plus. I join them with an or. So I look at this circle, and this time I'm going to look at this column in this row, and I figure out what do they all have in common. Well, they all have a 1 for y2, so that's y2, and they all have a 1 for w, so that's w. Yep. Now, if it was they had a 0, then it would have been a w bar. And then I just factored out the w. Okay, so now we're going to look at the z. Now remember, the output depended only on the input. I'm sorry, only on the state. The output depended only on the state. And if you go back and look at your state assigned table, we had an output of 1. So the state assigned table is in the order of y2, y1. And when we had y2, y1 was 1, 0, then we had an output of 1. So when y1 is 0 and y2 is 1, we had an output of 1. And when they were both 1, we had a D, I don't care. And otherwise we had zeros. And so Z is going to equal y2. We have our states are defined with 2 bits. That means that we're going to need 2 flip-flops. So however many numbers you're using to define your states is how many flip-flops you're going to have.
What is W, the number of states? Is like 0, 1?
No, the number of states is, so we have 3 states, but we used 2 bits
Oh, okay.
to identify them. So I don't think I said that clearly. However many bits you needed to identify them, that's how many flip-flops you needed.
Okay.
So we used a 2-bit number, and so that's how many flip-flops. Okay, and I will have, it'll be D, and we'll have a clock, and we'll have Q, and we'll have Q bar, because we'll actually use Q bar. We'll have a clock. And this will be Y2 in and Y2 out. And Y1 in and little y1 out. Now we know already that Z was Y2. So I can just go ahead and say, here's Z. Got that. Okay, and then we said Y2 was W times Y1 plus Y2. So I'll have okay, so I believe I just made y1 or y2. That's this part right here. I have w, that's an input, and I need to AND it with that. And I think that works. And our y1 was W, Y1 bar, Y2 bar. So I will have a 3 input AND gate with W. I am the worst at these. And that's Y2 bar. And that's Y1 bar. And then if you don't want to put the clock in on your drawing, he's fine with that. You just say you omitted the clock because it was making things messy. But you should say that you omitted it. Clock and yeah. Okay, questions on that? Okay, so now we're going to look at a timing diagram for our given values.
Oh, I'm sorry. Can
Yeah.
you go back 1 second?
Sure.
Thank
Do y'all have professors who are like, don't take pictures?
No, I don't think I've ever had a professor.
I have, and it's just like, but you're going so fast. How you can come to my office and look over the notes. It's like every day. Okay. Okay, everybody ready? Okay. All right. Complete the timing diagram for the given values of W. So what you need to remember here is that you're going to be looking at the previous values to figure out what your output is. So let's remember Y1 equals W, Y1 bar, Y2 bar, Y2 equals W, Y1 plus Y2. And I found, for me, the easiest way to do Z was just to remember how Z was defined. Z was defined as it would be 1 if the previous 2 inputs were 1, and it'd be 0 otherwise. So I'm going to do Z first. So at each clock cycle, look and see were the previous 2 inputs 1? Nope. Nope. Because the way the machine was defined at the beginning of the problem was that the output was 1 if the previous 2 inputs were 1. Otherwise, the output was 0. And for me, it was easier to just look at my input W right here and just look at that and see when the previous 2 inputs were 1 rather than trying to match it up with my equations. So when I get to, let's see, T1 to T3, I still don't have my previous 2 clock cycles, R1. And not until I get to T5 are my previous 2 clock cycles 1. And so at T5, my previous 2 clock cycles are 1. So I look back. So I'm right here. I look back, and I see that the previous 2 were 1. And now that I'm here, I look back and say, no, it's down to 0 again. And now I look up here. Now I've got 1, but not 2. And then now, when I look up here, oh, my previous two were 1, so that's good. And then I look up here, previous two were 1, so that's good. And then I look here, now it's back to 0. And then up here, no. So that's what Z looks like. Okay. So now, notice that, and this is just going to be a little bit of a shortcut, both Y1 and Y2 have W anded to something. So that means if W is 0, the whole thing is 0. But also remember, we're always looking at the clock cycle before. So when the clock cycle before had a W equal to 0, then we know Y1 and Y2 will be 0. So like right here, right here. So clock cycle before was 0. I'm going to skip this one because I don't know yet. I know right here it'll be 0. I'll skip here, skip here, skip here. I know right here it'll be 0. And right here it'll be 0. So I just went through and just put in 0 where I knew it'd be 0 where the previous clock cycle had 0 for W. So now all the ones I have left have W equal to 1. So I can just look at the other part of my equation here to see if I'm going to have 1 or 0. So when I'm looking at this clock cycle right here, I know W is 1 because I marked all the ones that were 0. I look at the previous two clock cycles and I determine what Y1 bar and Y2 bar are. Well, Y1 was 0, Y2 was 0, so Y1 bar is 1, Y2 bar is 1. So Y1 bar times Y2 bar is 1, so this gets me 1. Now I'll look down here to Y2, and I'll look at the previous clock cycle. Here I have Y1 or Y2. So is either Y1 or Y2 1? In the previous clock cycle, is either Y1 or Y2 1? No. So basically, Y1 will be 1 if Y1 and Y2 are both 0. Because if Y1 and Y2 are both 0, then Y1 bar is 1 and Y2 bar is 1. Okay, so now let's look at this clock cycle right here. And in the previous clock cycle, were Y1 and Y2 both 0? Yeah, so that'll get us a 1. So, on the other hand, were either of them 1? No. Okay, now right here, in the previous clock cycle, were both Y1 and Y2 0? No, because Y1 was 1 and Y2 was 0. So that's going to be a 0. And then for Y2, was either Y1 or Y2 1? Yes.
Wait, for the one we just did, so that's looking at T3 and 4, or just T3 or T4? Which one is it looking?
The one I just did
Yeah.
is looking just at the one I just did looked just at this column, just at the one coming before. When I did Z, I looked at the two previous ones. When I'm doing Y1 and Y2, I'm looking at just the previous one.
Okay. Okay.
Okay, so now for y1, are both y1 and y2 0? In the previous clock cycle? Yes. So are either of them 1? No. Okay, in the previous clock cycle, are both y1 and y2 0? No. Is either of them 1? Yes. And then here, are they both 0? No. And is either of them 1? Yes. So now we're going to repeat steps 6, 7, and 8 if the states are represented as shown in the following table. So here we're just having a different state assignment. So last time we said, A was 0, 0, B was 0, 1, C was 1, 0, and then we had a don't care. So this time we're changing it and we're making C 1, 1. So we still had our state table that looked like this. Okay, so we still had that. So our Z is going to be the same. And our row that we're not using, those are going to be don't cares. And now we're going to replace all of the A's with 0, 0. We'll replace the B with 0, 1. And the two C's with 1, 1. Okay, so now let's derive an expression for y1. So remember, we're looking just at the second column. And this is supposed to be W. And when we have 1, 0, we have don't cares. Otherwise, when W is 0, we have zeros. And otherwise, when W is 1, we have 1s. So this makes for a nice expression that just says y1 equals W. Okay, so now we'll do Y2. And we have don't cares for 1, 0. And when W is 0, for the others we have 0. When W is 1, we have 0 for 0, 0. And we have 1s for the other two. So that will be our expression. And Y2 will equal Y1W.
I'm sorry, why didn't you, okay, wait, I apologize, I thought that was I saw it wrong.
Wait, so are both these state, like this state table and the one from like the first page, are they both equivalent?
Are they both what?
Equivalent?
Yeah, yes, they both describe the same machine. They're just, we're just going to see that if we do it this way, we get a simpler circuit.
Okay.
But there's no way to tell ahead of time what's going to be best.
Okay.
And then let's look at Z. Well, I'll go ahead and do it. Okay, so I don't know if y'all can read that Carnot map over there. So for Z, it's we have that, and so I can get this expression. This top was Y2, so this tells me Z is Y2. So now I have Y1 is W, Y2 is Y1W, and Z is Y2, and we can see would make a simpler circuit. Yeah, let me add a new page. Okay, so we still were using 2 bits to define our states, so we're still going to have 2 D flip-flops. And I'll call this one Y2 on top and this one Y1. And we have W. And Y1 equals W. So there we go. That's it. So that's Y1. Y2 equals Y1 and W. That's Y2. And Z is Y2, so that's Z. And then you have a clock. So it just gets us a simpler circuit.
So why exactly would we only have 2 flip-flops again?
You look at the number of bits that you use.
Oh, so because it's Y1 and Y2?
Yes.
Okay, alright.
Yep. One of them is going to give you your y1 and one gives you your y2.
Right, exactly.
Yep. And so, for example, on this next one, we have 3, and so we would have 3 flip-flops. So this says one hot encoding. One hot encoding means that of your number, only one of them is going to be a 1. Everything else will be a 0. So A is 0, 0, 1, B is 0, 1, 0, and C is 1, 0, 0. And if we remember our state table, which I don't, our state table was so now we can just fill this in with how they're defined. So A is 0, 0, 1. B is 0, 1, 0. And C is 1, 0, 0. And our output is 0, 0, 1. And I'm not going to go through the process of making Carnot maps for each of these, but let's see if we can kind of look at them and figure out what they're going to be. So let's look at Y1. Y1 is 1 when W is 0, and it's 0 when W is 1. So Y1 is W bar. Y2, well, we can see that Y2 is 0 always when W is 0. So we can AND W to something. Because if W is 0, it'll be 0. And then we'll look over here to see what we want to AND it to. And when is Y2 1? It's 1. Oh, actually, I wanted to look over at the present state. That's what I wanted to look at. So I want to look at these right here. So it's 1 when Y1 is 1. And then Y2 is also going to have a W ANDed with something. And we see that it's 1 when Y2 is 0. Wait, no. Oh, I'm doing Y2 again. Hold on. What do I want to be doing? I want to be doing Y3. Thank you. So W. So I want to be looking at Y3. And Y3 also has W's here. And then it's 0 when Y1 is 1 and 1 otherwise. So that'd be Y1 bar. and z is the same as y3. And you don't have to be able to do that. You can do Carnot maps. I just didn't want to do more time with Carnot maps. Okay, so explain how this state diagram is different from the one in number 4. Okay, why is this a Mealy type finite state machine? So how is this different from the one we did before? We go back and look. Let's look at the one, our first state diagram. Where did we put the output? In the circle, because the output depended only on the state we were in. Here, we put the output with the little arrow because it depends on the input as well. So each arrow is going to have both the input and the output on it. So let's see what this says. So this is saying if I'm in state A and I get a 0, I go back to state A. So let's say that's a state. If I'm in state A and I get a 1, I go to state B. So state A have 0. State B, I have a 1. Now, if I get a 0, I go back to A, which means I have a 0. If I get a 1, I go back to B, and I still have a 1. But I can use this still to determine my output, because if I go from A to B, I had a 0 and I got a 1, I don't have 2 1s yet. But if I'm in state B, I have a 1, and if I get another 1, then now my output is going to be 1. So this machine only has 2 states. So a Mealy finite state machine will have fewer states than a Moore machine. So we don't actually have a state here that represents having 1, 1. We have a state that represents 0 and a state that represents 1. And then if you get a 1 on that 1 state, then your output is 1, and you still have a 1. So the table is going to be the same idea. It's the same behavior. So y'all see if you can fill in the table with knowing that it's the same behavior. If the previous 2 inputs are 1, you get a 1. Otherwise, it's a 0. So see if you can fill that in. Something's wrong. Yep. No, it's not right. I did this wrong. Sorry. This is not right. I told you wrong. So this is a Mealy machine, so it does depend on the inputs, so we're actually not looking at the previous input. We're looking at the current input. I am very sorry. We're looking at the current input. And so if the current one and the one before are 0, so that's 0, 0, 0, 0, and then this is going to be 1 because the current input and the one before, and 0, 0, 1, 1, 0, 0.
What was this called again?
Mealy, as in like meal with a Y. Yeah, so that's the difference, and so I hate that I said it wrong first. So with the Mealy machine, you're not, the current input is important, and that's what defines a Mealy machine. Okay, so our present state, we just had our two states. We had our A, let me go back. Here's our diagram. Okay, so here's our diagram. If our present state is A and W is 0, then our next state is A. If our present state is A and our W is 1, our next state is B. If our present state is B and W is 0, our next state is A. If our present state is B and W is 1, then our next state is B. And we have outputs of 0 on all of these except for, looks like I didn't write it here, this last one is W equals 1 and Z equals 1. So when W equals 0, your output is definitely 0. And when W equals 1, your output will be 0 unless you're in state B, and then your output will be 0. Okay, so now what's cool about this is how many states do we have? 2. How many binary digits do you need to represent not the number 2, but 2 different things? Yeah, you just need 1, because you can have a 0 and a 1. So that means where A, will let A be 0 and B be 1. So then we can just fill these in with 0, 0, 1, 1. And these were already numbers 0, 0, 0, 1. And now we want to draw a circuit corresponding to this finite state machine. We just have one bit here, just Y. So we just need a single flip-flop. We didn't synthesize anything. Just do it real quick. Okay, so we have Y and W, and when W is 1, Y is 1. So this tells us that Y equals W. And then Z when Y is 0, we get 0. When Y is 1 and W is 1, we get 1. Otherwise, we get 0. So Z is WY. So here's our flip-flop. W is D. So this gets us little y. And Z is the AND of this and W. That's a lovely AND a clock. Okay, so let's go back to the last one. So after I've been writing for a while, it's like my pen starts to lag a little bit, so it's good that we're on the last one. Okay, so remembering how the melee works, our output is going to be 1 whenever our current input is 1 and the one before it. So that's Z. Z is our output. So we'll go across here and we'll get a 1 right here at T4 because we have an input of 1 and the previous one was 1. And then again at T7 and T8. And that's it. Okay, now we said, I had it on a different page. What did we say Y was? Y was just W, right? Okay, now Y is going to be a clock cycle behind because it's coming out of a flip-flop. So it's going to be what was in the flip-flop ready to go, and then it will be one clock cycle behind, unlike the Z output. So Y is going to be W, but it's going to be just lagging by 1 clock cycle. Okay, so are there any questions?
Yes.
Okay.
Okay. How did you, can you explain again for number 12, how you know the meaning?
Okay, so if you look at the diagram for number 12, you see how inside the circle I don't have an output? So the output depends just on the state. So you just put the output right there in the circle that represents the state. But for Mealy, the output depends not just on the state, but the input. So you put it on that little arrow saying, here's the input, I was in this state, here's the output.
Oh, okay. That makes sense. Thank you.
Other questions? Yes?
What is the hot and cold?
The one hot, that just means that when you have your numbers, so I would have these would be the numbers that I would use for 4 different states. Each one of them has just a single 1 in it. That's what one hot means. It's just one of them is hot. And so it's just that's what it means. Yeah, he had used that on some question at some point, so I threw it in here. Not on a test, I don't think, but on homework at some point in the past 7 years. Yep. Other questions?
Can you go back to 15?
Yes.
So, how did you find like the corner map for W and Z?
Okay. So
Which W and Y do you look?
I'm sorry.
Like at which W do you look at the next state or the other?
You do the present state. So here's